Awesome. Well, hello, everyone. I am delighted to welcome all of you who are here in 3 dimensions, as well as all of you who are on Zoom, to our KNI Distinguished Webinar / Seminar. We have a very special speaker today who traveled all the way from the very cold place called Chicago, from Northwestern University, Professor Chad Mirkin. So Professor Mirkin is the director of the IIN, so that's the International Institute for Nanotechnology. And he's a professor of chemistry, chemical and biological engineering, biomedical engineering, and material science and engineering, and also professor of medicine. I don't know how you acquired so many titles, but I think I got all of them right. So Chad is a chemist and a world-renowned nanoscience expert who is known for his discovery and development of a spherical nucleic acid, SNA, and SNA-based biodetection and therapeutic schemes. The invention of dip pen nanolithography, so that's DPN's acronym that many of you have probably heard of, and related cantilever-free nanopatterning methodologies, on-wire lithography or OWL, coaxial lithography or COAL, and contributions to supramolecular chemistry and nanoparticle synthesis. Chad has authored more than 825 manuscripts and more than 1,200 patent applications worldwide, and the founder of multiple companies, including AuraSense, Execure, TerraPrint, and Azul 3D, which is my favorite, of course. Today, we are very lucky to hear Dr. Mirkin sharing with us his group's recent work on colloidal crystal engineering with DNA. Of course, we are familiar with DNA various capacities, and DNA represents a powerful programmable tool for bottom-up material design. His group has shown that DNA and other nucleic acids can be used as highly programmable surface bonds to control the spacing and symmetry of nanoparticle building blocks in a structurally sophisticated material. It's analogous to a genetic code for materials assembly. We're delighted to hear about your work. And before we begin, I'd just like to remind all of you who are online to submit all of your questions via Q&A, and I'm going to keep track of them, and then we'll read them off at the end. And with that, welcome, Chad. We're delighted to have you here, and thank you so much for coming.
I said this is a first for me, giving a hybrid talk. It's great to be back on the road again, at least getting a feel for being back on the road, even though I have to do it through the mask. But I think this is a step in the right direction. And I always love coming to Caltech. One, because the students are absolutely fantastic, and the science is spectacular, and it's just so much fun reconnecting with all of my good friends here, and today was no exception. I thought today, given the fact that this is a Kavli lecture, I would focus on a real problem in nanotechnology, but one that has a significant thread involving chemistry, biology, and material science as well. And that's an effort that we've been working on for quite some time, which I like to think about as a new way of thinking about chemistry. Building materials from the bottom up, learning how to program matter from elementary building blocks, not atoms, but particles, and using different types of bonding mechanisms, in particular ones that utilize the blueprint of life, DNA and RNA. I like to say that everything we do starts with one tiny particle. And that's what Julia was referring to, a spherical nucleic acid. We kind of happened upon this about 25 years ago now. In fact, we didn't even think about it as a spherical nucleic acid at the time. We actually thought about it as a programmable atom equivalent. We were trying to create a new way of programming matter by interfacing oligonucleotides with particle building blocks. A spherical nucleic acid is exactly what it sounds like. It's an arrangement of oligonucleotides in spherical form on a nanoparticle core. It has no natural equivalent. Interestingly, when we first coined the term spherical nucleic acid, it was really aimed to be descriptive. But I thought, that's odd. I mean, you just don't think about this type of architecture at the time. And sure enough, it was one of the few things you could put in Google. Harry was visiting. I don't know if he remembers. I actually told him, I said, you're going to hear this term, and this is going to be very, very important. Remember it. And of course, he made fun of it. I think he remembered it. And it's become pretty big. Now there are literally millions of hits if you turn in, type in spherical nucleic acid. And the reason it wasn't in there was in nature, we have linear, we have circular, and we have all sorts of folded forms of nucleic acids. But a spherical nucleic acid is made purely through chemistry and concepts from nanotechnology. But it's more than that. When you make this type of architecture, this type of arrangement of nucleic acids, you get a structure that behaves very differently from those linear and other natural forms of DNA and RNA. The pre-ordering of the oligonucleotides leads to a structure that binds to complementary oligonucleotides up to 100 times more tightly. You might say, well, big deal, why does that matter? Well, it turns out that's really important if you use these as probes, for example, in molecular diagnostics, which they are used today. For example, the Verigene system, which in fact has tests for all sorts of infectious diseases developed by Luminex, actually originally by Nanosphere, a company that we started, is used in over half the world's top hospitals, and is used because these types of particles are very sensitive probes for oligonucleotide signatures associated with disease. And in chip-based formats, you can turn them into panel assays that are in fact used for even things like COVID all over the world. These architectures on a sequence for sequence basis are completely different from their linear cousins. Another example of that is nucleic acids don't naturally enter cells. These structures do. They don't require co-carriers. They don't require things like lipofectamine, any sort of transfection agent. So if you expose almost any cell type to spherical nucleic acids, they're recognized by things called scavenger receptors and rapidly internalized into those cells. Well, that's a big deal, not only because it's fundamentally different, but because it's enabling. Now you can get large amounts of nucleic acids into cells, and you can use that capability to develop techniques that allow you to measure, for example, intercellular contents. In fact, we've developed structures called nanoflares based upon spherical nucleic acids that are designed to go into cells and recognize nucleic acid signatures, RNA, for example, and if overexpressed, bind and release a signature that turns on when that signature moves away from the gold nanoparticle probe, which is the core in that particular case. That turns out to be, at the time, the only way of measuring the genetic content of live cells. So if you couple this with flow cytometry, this is a way of sorting out cells, for example, finding cancer cells in a sea of healthy cells, rare cells, for example, all based upon differences in genetic content. It turns out this ability to get nucleic acids into cells without co-carriers is really important in thinking about developing therapeutics. RNA, of course, is in the news with the vaccines, but the idea of nucleic acid medicines has been around for 30 years. One of the biggest limitations, though, is how do you get nucleic acids to the areas they need to go? Well, these types of structures, if directly delivered to tissues, skin, for example, or cells, are rapidly taken up by what they encounter. And so you can use that to create all sorts of therapeutic shots on goal. And now there are now clinical trials, I think 6 to date, 3 for skin disorders, 2 for cancer immunotherapies, and 1 very exciting one for treating GBM, glioblastoma multiforme. It's one of the few systemically delivered spherical nucleic acid therapies. These cross the blood-brain barrier. And that means you can think about flipping genetic switches in those cells that cause, for example, cancer cells to selectively die. I like to always start with that because it allows me to talk about something that has no real technological driver, at least to date. I think it ultimately will, and I want you to think about that, but it's really why we got involved in this in the first place. And that's outlined over here on the left. When we first started doing this, we said, hey, let's learn how to, again, think of particles as atoms and oligonucleotides as programmable bonds, and ask the question, can we begin to create design rules that allow us to build structures at will from the bottom up? And you might ask, why do you want to do that? Well, I think it's, first of all, a great chemical challenge. Colloidal crystals are really interesting structures that have phenomenal properties that depend upon some of the parameters that are important here, the crystal symmetry, lattice parameters, so the interparticle distance, call that bond length, the composition of the particle building blocks, the elements, if you will, the crystal habit, what shape they ultimately form on the macroscopic scale, and even reconfigurability, right? These are not electron-based bonds, they're molecular bonds, so you can think about using chemical triggers that control, for example, the spacing between particles, the size of the crystal, the volume of the crystal. And it's really getting at this question, how does one program structure from the bottom up? Why might that be important? Well, just turn to nature. Nature uses colloidal crystals for all sorts of things, mostly colors. Colors from opals, from the insect wings and bodies, all a result of controlling the type of colloidal crystal that gives that particular color. even berries. And lots of people, including many people here at Caltech, have thought about now using these for anatural purposes. For example, guiding light and controlling the movement of light for creating photonic circuits. You turn again to biology, a really cool thing that you can think about doing is creating reconfigurable systems. So for example, a type of camouflage, the squid skin is an example of a colloidal crystal that's stretching it, allows you to control the distance between the particles and ultimately the interaction with light and the color that's observed. Very important in terms of camouflage. So here's what I want you to think about. I always like to set up a straw man, because this is the way I think about developing this whole field, because this became a field and one that not just us, but many people pursue, as you'll see in a bit. So with conventional chemistry, we work with atoms and electron-based bonds. We make molecules. And for guys like Bob Grubbs, we learn how to zip those molecules together in very effective ways and make materials. And to lay everybody's concerns, I'm not here to tell you we're putting a chemistry out of business. That's not the goal here. I look at this as a straw man to ask, how far can we go with this concept of particles as atoms and oligonucleotides as bonds? Where do we fall short? And where can we go beyond conventional chemistry? So that's the idea. Now, the thing I want you to keep in mind here, particles are available now in many different forms. I'm going to talk heavily about inorganic systems, but nature has particles that we often call proteins, and lots of different ones, and those can become the basis for different building blocks, and I'll touch upon that as well. Programmable bonds are our oligonucleotides, and so the question is, how can we do this in some sort of orchestrated, designed way, not by happenstance, but by design, because that's what we're ultimately after. Well, I got started in the early days with a guy named Bob Letzinger. Some of you know, Harry knows him. Really just a titan in terms of chemistry. He invented a lot of the chemistry that made the synthesis of DNA possible. Great thing about Northwestern, we collaborate a lot. I sent one of my postdocs down, or actually grad students at the time, and said, you know, go find out from this guy Letzinger how we can make oligonucleotides with alkyl thiol N groups, because I want to interface oligonucleotides with particles, and I want to test this idea. So we quickly did that, and we built what now I would call would be the first spherical nucleic acids. This is back in 1996. We synthesized particles that had designed sequences, and then we introduced oligonucleotides that would allow them to come together and form this, in our eyes, this beautiful crystalline type of architecture. But we didn't get that. In fact, looking back at this, I'm amazed this was even published in Nature. It's published in Nature, though, because of what it was at the time. So this was bringing together two very different fields, right? Using oligonucleotides as a programmable bond to control the formation of materials. And what we got were these aggregate type architectures. Now, we knew DNA was doing the work, and we proved it. Because if you have a specific sequence, that sequence has a melting profile that depends upon the length of overlap, the complementarity, and whether or not it's AT or GC rich, which we could design. And so we could move that melting temperature all over the map based upon the choice of oligonucleotides. We knew it was reversible, and there were spectacular optical property changes that accompanied this. A guy named Bobby Music did this work early on, and you could watch as the oligonucleotides were added to bring the particles together. They'd go from this deep red color to this, what we called Northwestern purple at the time. And if you put it in an oven and went above the melting temperature, the DNA would unravel, put it back on the desk, it'd come together. And what we were looking at were the plasmonic properties of the particles amplifying the hybridization event, the recognition event involving DNA. And almost immediately, that's when we got the idea of moving these towards biological detection systems, because this was a really cool way of visualizing that recognition event. But they weren't the fantastic structures that I alluded to. This is what we make today. This is a rhombic dodecahedron crystal made from gold particles as well. The right types of oligonucleotides. I'll talk about what right type is in a second. It'll form 100% of the time. It is the thermodynamic sink. The DNA is placing the particles, all the particles, everywhere they should be, doing all the work that we had intended, and producing that at the end of the day, as I said, 100% of the time. About 2 million particles make up this size crystal. So you might ask, why can you do that today and it didn't work back then? The reason is we understand more about the bond. We understand more about the atoms now. And one of the important thing here is the design of the oligonucleotides. We have to have an anchoring group. That's the thiol, for example, for gold, but you can use other types of chemistry. It's ligand chemistry. It's a coordination chemistry, if you will, for controlling how oligonucleotides interface with these particles. This controls the length, the bond length, the distance between the particles. That's tunable. Made thousands and thousands of crystals using this particular approach. And then this is key. This is a sticky end. In the early days, we used what we thought we needed, long sticky ends, because we needed enough of an interaction, we thought, to bring these together. But that's amplified, that's magnified, especially as you get bigger and bigger particles, because you get cooperativity. So you actually don't want long overlaps because you get stuck in kinetic traps. The system never falls into the thermodynamic sink, which is the crystal. But if you make these relatively short, for example, 4 bases long, you now have a strong enough interaction to bring the particles together, but a weak enough one to allow the system to equilibrate under the conditions of the experiment. And that allows the DNA to do its work and to begin to place the particles where they need to go. Well, that's pretty powerful. So the question we've been asking is, can we develop an understanding of how to build with these elements like we do with atoms in traditional chemistry? And Harry knows that when we think about at least teaching at the freshman level, we think about the importance of this guy, Gian Lewis, who began to come up with concepts to understand how different types of structures could form. And we all know about Lewis dot structures and the octet rule. Are there any parallels between this type of analysis and what I'm talking about here? That's one of the things I want you to think about. Well, let's talk about the differences. So our atoms are particles, our bonds are oligonucleotides. One of the things that's important here is, and this was a key in figuring out how to really do this by design, is there's a key difference here. And that is the bonding element in this type of chemistry is separated from the atom identity. The DNA does not care about the compositional identity of the atom, of the particle. It only cares about the size and the shape. That's not true of conventional chemistry. If I pick different atoms in the periodic table, I have different constraints in terms of bonding. I just have to live with that. The fact that they're separated gives me a level of predictability, a level of design, as you're going to see, that goes beyond conventional chemistry. So I can make any set of interaction pairs interact based upon choosing the right types of oligonucleotides. And I'm going to show you that many, many times over. So the key here is, because we separate bonding element from atom identity, is we can independently control the size, composition, and shape of the atom or the nanoparticle, and the characteristics of the bond, the sequence, the length, and the density. Density is important because this doesn't work unless you have high density structures on these particles, because that forces the oligonucleotides to stand upright and adopt the central shape, or the shape of the central particle core. Okay, I'm going to bring you guys up to speed so I can share with you really what's exciting in terms of the current capabilities, because I've talked about this even at Caltech in the past to some extent. The bottom line is we've now begun to utilize this to develop a whole series of concepts that lay the foundation for, as I said, a new form of chemistry or structure control. A key part here is something called the CCM. I'll come back to that in a little bit. We call it the complementary contact model. That basically says that particles will arrange themselves in space to maximize contacts that will lead to hybridization. It's a bonding argument that if I have a set of particles that can form a crystal, the particles will arrange themselves to maximize hybridization and maximize duplex formation. If you accept the complementary contact model as a guide, you now can begin to design based upon geometric arguments. You have a set of particles, find sizes and shapes. How can I, and with oligonucleotide end groups, how can I arrange them to maximize duplex formation? That turns out to be quite powerful. I'll give you a couple of examples of that. I've already mentioned the atom is independent from the bond. Here's the one thing I want you to think about. The other advantage of this type of chemistry in terms of capability is we're not using electron-based bonds, we're using molecular bonds. So it's a functional bond. And I can use that to begin to trigger conformational changes that allow me to control crystallization paths or to change the structure of a particular crystal after it's formed. Valency, directionality, We don't have hybridization, but we have particle shape. So if I want an octahedral arrangement of oligonucleotides, I use a cube. We'll talk about other shapes as well. And the fifth thing that's important here is the design rules that I'm going to share with you allow me to dictate symmetry, crystal habit, which the best chemists on Earth can't predict with a new molecule, for example. I'm going to show you we can do that because we know these are thermodynamic products. We can model it. And lattice parameter. And I can tailor that with a oligonucleotide length. Okay, so let me give you a feel for how the complementary contact model works. Let's say I would like to have an FCC lattice. Okay, think backwards through that. I'd like all nearest neighbors to be able to bond with the central group, 12 nearest neighbors. I want a self-complementary particle. I can make that by terminating and creating a sticky end that's GC-GC. Flip that around, that's CG-CG. And that will form every time. If I want a BCC or cesium chloride type structure, I'd like an AB structure, right? Two particles the same size, but I'd like oligonucleotides that are complementary to one another, not self-complementary. That gets me 8 nearest neighbors. If I want to begin to play and access different types of lattices, I can play with the radius ratio rules and how they fit together. And the complementary contact model will pick then different types of targeted architectures. So here are examples. FCC. This is small angle scattering. We do that at the synchrotron. The simulation is below. You can see the TM images over here that we collect after we embed these in things like silica. You have to lock them into place to be able to see them by electron microscopy. But you can see all these. So the FCC, cesium chloride, BCC, AlB2 here. Cesium 6C60, how do you get that? That's 1 big and 6 small. So you play with the size ratio. I think there's chromium silicide. That's 1 big and 3 small. So all these were made by design. So it wasn't we made them and characterized. We actually targeted them based upon adjusting these and using that geometric argument that we define as the complementary contact model to get there. Okay. In my view, as I teach general chemistry, is that the CCM is the DNA equivalent of the octet rule. So I think of the oligonucleotides as unpaired electrons, and I think of the duplexes as paired electrons, right? And the system wants to maximize that pairing. We don't get to 8. We try to maximize whatever the contacts are that lead to hybridization, and that leads then to the most stable architecture and the one that you're ultimately going to predict. To bring you up to where we are, we now have built a capability that allows you to make 78 unique lattices to date, everyone structurally characterized. Many of these, several, I think 5 or 6, have no mineral equivalent. So beginning to make structures where I can't find an equivalent in nature. That's kind of interesting from a chemistry standpoint. It's always one of the things you're trying to accomplish in terms of structure control. Even quasi-crystals, as you're going to see in a bit. Okay, so how do I think about this? Our table of elements is not the periodic table of elements. It's the number and types of particles that are available to us. And there are many, a lot more than the conventional table of elements. Defined by composition, so metals, semiconductors, insulators. You can have hard structures and you can have soft. Organic cores, micelles, liposomes, even proteins, when modified, can be turned into spherical nucleic acids and programmable atom equivalents. And then MOFs are a nice example. If you can make them in nanoscale form, which we've developed a whole series of methods, you can turn those into an almost endless supply of different types of building blocks that can be used in these types of strategies. Okay, you have to get clever about how you build architectures if you want to keep expanding the number of possibilities. So I want to kind of take you through some of that so you can kind of think or follow at least the thought process. So one of the things we pushed hard on for a variety of reasons was to learn how to develop a spherical nucleic acid that was coreless. Because really what I've described is a spherical nucleic acid nanoparticle conjugate. So we had a challenge in the group to make one of those. And we did that by cross-linking the oligonucleotides. I won't go through the chemistry there, dissolving the gold core. But when you do that, you basically just fill that up with solvent. And you've got now a hollow programmable atom equivalent. That's important on the biology side of things for a lot of different reasons. I won't go into those right now, but it's also important here too, because I now can use this to hold lattice sites that allow me to make different arrangements of inorganic systems. And so here's the thought experiment. If I have a BCC or cesium chloride type lattice, right, that's the AB structure, and I replace one of these gold particles with a hollow spacer, this goes from BCC or cesium chloride to simple cubic. Well, here it is. This is with gold. This is cesium chloride BCC. This is with the hollow spacer, simple cubic. Remember, the hollow spacer is silent to the X-rays. So we're able to transform, at least from an inorganic standpoint, that lattice. Well, that's kind of simple, right? But what about ALB2? Well, if I replace the small guys, the B, the two, right, small ones, with hollow, this becomes simple hexagonal. If I replace the big guys with hollow, this becomes graphite-like. Cesium 6C60, that's, remember, 1 big and 6 small. If I replace the small guys with hollow, that becomes BCC. If I replace the big guys with hollow, that becomes lattice X. That's the first structure that has no mineral equivalent. It was Evelyn I. Young discovered this. I told her she missed an opportunity. She should have called it lattice E, but I think we published it as lattice X. Okay. So far, what I've talked about, and I'm telling you chronologically, is we're making crystallites. We're not making single crystals. I showed you one, but that was really taken down the line. How did we get to single crystals? Well, I kept thinking about this, and I said, look, you know, we know, the cool thing about this is we know the bonding characteristics. We know the strength. We can pick conditions where we can make the on-off rates fast. So let's sit right up at the melting transition of the DNA holding these particles together and see if we can anneal out all the defect. And it turns out that doesn't work. That makes better and better polycrystalline structures, but you don't get single crystals. Take a page out of the organic chemistry literature, old school organic chemistry literature, and say, let's super saturate the solution, elevate the temperature, and then slowly, so we build an instrument that allows us to slowly take this through the melting transition, so the cooling transition in this particular case. What's amazing is if I take the two particles that are the same size and complementary to one another, designed to give me the BCC structure, 100% of the time, it will give me this rhombic dodecahedron structure. The reason is very simple. That is the Wolf construction. That is the thermodynamic sink. That experiment was critical. We published that actually in Nature because that not only validated that you could get single crystals for the first time, but it validated this concept of the complementary contact model. Now, the complementary contact model is not a law. It's just a rule. And it works greater than 90% of the time, at least in our hands, of all the different types of structures. And when you accept that, you have a very easy design path. If you have to take into account entropic contributions, which we do in certain cases, then all hell can break loose and you lose a lot of the predictability that I'm talking about. So we try to work with systems where the complementary contact model is in play so that we have that level of predictability. Now, I haven't told you how we stabilize these. A lot of people say, well, how aren't, you know, it's DNA, it can't be that stable. And it's true, they're made in solution. If you dry them out, they just collapse. But if you grow silica around them using sol gel type processes, you can encapsulate them in silica matrices, and now the particles are locked into place. You can actually burn out the oligonucleotides after the fact, and you can use then the captured lattice for all sorts of different purposes. We've generated catalysts that way. We've recently figured out there are ways to get rid of the silica. You don't need to use silica in certain cases. You can use, for example, silver ions will intercalate into DNA between the bases. Intercalation is a bad term. It's actually coordination chemistry in this case. Locks the oligonucleotides into place and takes these from low temperature materials to relatively high temperature materials, things you can boil and they won't come apart. Now, there's some positives and negatives. Here you get residual silica, and that kind of blurs a little bit what you've made in terms of characterization. Here, I show a contraction because that leads to a contraction of the oligonucleotides. So you're getting a contracted version of what you've generated. But I just want to show you how powerful this is. This is, you know, showing you there's no cherry picking going on here. This is the BCC structure. We've locked it into place with the silver ion, and you can see nothing but rhombic dodecahedra. There's a larger field of view there. DNA is the best test for whether or not you have high quality particles or not. because I can guarantee you that if you choose the oligonucleotides properly and have high quality, meaning monodispersed particles, you will get crystallization. It does its work, which is really quite powerful. So now we have methods to synthesize large batches of uniform colloidal single crystals in monodispersed form. I know a lot of physicists here at Caltech interested in metamaterials. These types of architectures can become the basis for devices themselves, where you can begin to study light matter interactions in unusual ways. I'll comment a little bit of that towards the end. Okay, this idea of programmable atom equivalents is interesting, and I talk about oligonucleotides as programmable bonds. One of the things we recently discovered with Monica Olvera de la Cruz is that when you keep shrinking down the size of the particle, something interesting happens. There is a duality that comes into play, where we go from what we call a programmable atom equivalent becoming a programmable electron equivalent. What do I mean by that? Well, in this model that I've given you, the DNA arranges the particles in space, and they are locked into space in particular lattice sites with the oligonucleotide tethers. When you have an electron equivalent, what happens is these become mobile within a sea of larger particles, a lot like bonding in metals. So the small particles, if they don't have enough tethers, don't get locked into place, and they roam and in fact randomize throughout the lattice defined by the larger particles. Well, that's kind of interesting because that's never been seen before in colloidal crystals, period. So that was a first. But the other thing is it really changes then how you think about what you can build and the properties of these types of materials depending upon what the building blocks are. So it keeps going. There are some interesting analogies, right? For example, to Vesper. We're familiar with the concept that a valence shell electron pair repulsion theory, and the idea that electron pairs will arrange themselves in such a way that you get defined geometries that lead then to different types of molecular outcomes. Does that happen over here? Because you could imagine that it might. Right? These tiny little particles might not just be completely randomized, they might begin to adopt certain positions around the larger spherical particle building blocks, which then dictates crystallographic outcome. It turns out that happens. So we've actually discovered a whole series of new architectures that are a result of these tiny little electron equivalents, not totally randomizing, but arranging themselves in specific geometric configurations that lead to or stabilize a particular solid state structure of interest. Now, it's kind of interesting how you look at these as either electron equivalents or programmable atom equivalents. A little bit depends upon the degree of mobility and conditions and the ways you characterize. But the point is that there's some striking similarities between this concept of programmable atom equivalents and electron equivalents and our conventional ways we look at atomic building blocks and electron-based bonding. Proteins, that's Mother Nature's building blocks. Does this work? Well, that would be interesting. I could think about using the design rules that I have here, because I know how to make lots of different types of crystal symmetries and program crystallization. The really neat thing about moving from inorganic particles to proteins is that I can only uniformly modify inorganic particles with bonding elements. With proteins, one is I get greater monodispersity. I can make a mole of protein particles that are all the same. I can't make a mole of inorganic nanoparticles that are all the same above a certain size. Two is I have a known chemical topology, so I can modify those in very selective ways, and I can control the number and placement of bonding elements on a protein surface, and that can lead to greater control in terms of crystallographic outcome. I can engineer proteins. I can place different functional groups on designer proteins that allow me to control where bonding elements are. So here's an example, mutant GFP. Mutant in this case, I can put a thiol on there that allows me to put in a oligonucleotide. I show it in color coding here. That's just to define length and sequence. I can have two different batches, two different oligonucleotides here, and I can take the periphery if these is amine rich, and I can modify with different oligonucleotides. So I can put one single oligonucleotide here and a different type of oligonucleotide here. Put an oligonucleotide here that's complementary to this guy, And now a different class of oligonucleotide is different from this guy. Why do I want to do that? Well, these two can be designed to pair up with one another. And now I have a Janus particle, molecularly pure, with two different faces, two different recognition elements, a linear type of architecture. That can be used then, for example, paired up with other building blocks. We know how to do that with inorganic nanoparticles, gold particles in this particular case. And you can see this is a layered type of architecture. And I can systematically control the distance between the layers simply by controlling the central oligonucleotide here and the length of it. So it gets me greater designer capabilities. I can take proteins and I can put two different types of oligonucleotides. For example, I can put one type of oligonucleotide in the equatorial belt, labeled as a weak interactor, and a strong interactor in the axial axis here. Why would I want to do that? Well, think about this. If I do that, that means there will be different conditions where I can trigger different types of bonding. So if I take this and introduce it to itself so that it's designed to recognize itself, I will generate these linear stacks. The weak interactions don't kick into play because the temperature, for example, is too high. But if I cool the temperature down, now the weak interactions can come in play, and these fibers will then assemble into belts that are mini fibers coming together. And so I guess what I'm trying to say is that we have a way of orthogonally controlling the chemistry, the placement of the bonding elements, using these types of building blocks that goes way beyond what we could do with at least the pure inorganic systems. So depending on what you want to do and what you want to make, those are key capabilities. Now, a lot of people ask, how does this all fit together? How is this different from, for example, origami and what people do in the quote DNA nanotechnology area? And there are two differences. One is these guys, for the most part, are focusing on making structures purely from oligonucleotides. They modify them after the fact with other things and decorate them, but the focus is on how do I make different types of nucleic acid architectures. The second is, and over here, this is really about using DNA as a smart glue, effectively, to build a structure that's primarily made of what we're calling the atom-based building blocks, the non-DNA-based building blocks. But the second is really important, and that is how we get to valency. So valency over here is achieved by creating rigid subunits through crossover type reactions that take squishy and flexible oligonucleotides, bring them together to form subunits that are rigid that then direct subsequent bonding events. Whereas over here, hybridization is not necessary. It's really the particle core and the dense packing of the oligonucleotides that forces the oligonucleotides to stand upright and adopt the central shape of the particle. So valency is critical in both cases if you want to make crystalline architectures. It's just you get there via two different paths, depending upon what you're interested in ultimately generating. So I want to show you that because we've tested that in great detail. And I remember I made that bold statement. I said, I can tell you if you have high quality particles or not. We don't want to fool ourselves and use a low quality sample. So we spend a lot of time trying to make really high quality particle building blocks. And here you can see different shapes: cubes, concave cubes, octahedra, tetrahexahedra, rhombic dodecahedra, concave rhombic dodecahedra, cuboctahedra, and truncated tetragonal prisms. These are some of the most monodispersed samples ever made. We know that because when we let them dry, they want to crystallize naturally. They have no oligonucleotide on them. We haven't forced any interaction yet. But if we modify them, we can begin to test this concept of valency. So as I said, if I want octahedral valency, I take a cube-shaped particle, modify it, and now that directs the formation of a cubic lattice. So now I'm controlling crystal habit. An octahedron forms a rhombic dodecahedron. A rhombic dodecahedron forms an octahedron. These are all the Wolf constructions. They're the thermodynamic sinks. They are validators that the complementary contact model is in play. But now I can force interactions that ordinarily won't take place. If I want small cubes and big cubes, I just modify them with complementary oligos, and this is the data over here on the right, you can see. Concave and convex, cubes and disks, these are circular disks. Imagine, how would you synthesize that with anything other than this type of oligonucleotide recognition element. It'll go 100% of the time. You can see the interdigitated structure. And again, the disks go right along the broad faces of the cubes because they want to maximize hybridization. That's the driving force in terms of this particular process. But you can get really sophisticated here. So I had another guy who's very interested, Wenji, in the group, very interested in how do I make dense structures? How do I get rid of a lot of the free volume of these types of systems? And he came up with this concept of shape complementarity. So if I match up particles of the right size and right shape, I can begin to fill the vast majority of the space available if I use really short oligonucleotide bonding elements. And it's remarkable. So in this particular case, where you use a cube octahedra and octahedra, you can force the formation of a densely packed rectified cubic honeycomb. And you can see here's the cartoon, and here's the data. Bitetrahedra and octahedra, you get this gyrated tetraocta honeycomb architecture. And these are amazing systems. And you can see the oligonucleotides doing their work, placing the particles where they should be. Tetrahedra and octahedra, that gets you this tetraocta honeycomb architecture. What about quasi-crystals? I used to get this asked all the time after the first paper came out. And I said, look, we can make a lot of things, but I doubt we'll ever be able to make that. Well, that turns out to be wrong. Because very recently, by taking structures with fivefold symmetry, right, got forbidden tiling issues there, we can modify them with self-complementary oligonucleotides. And we can drive through enthalpic interactions, the hybridization, the formation of a dodecagonal quasi-crystal, I have a hard time pronouncing that, that falls out of solution every single time. And this has been characterized out the wazoo, where you can see very clearly it has a 12-fold axis. Think of this as layered quasi-crystals. It's a periodic structure perpendicular to those planes. But this is truly due to the DNA interactions, because if I try to grow these from the same particles and simply use entropy-driven, either by simulation, Sharon Glotzer's done the simulations here, or by experiment, I end up getting this triclinic structure. So it's the forced interactions, the face-to-face interactions maximized through DNA hybridization that ultimately leads to this particular architecture forming. Okay, the other neat thing about this is I can control where bonding sites are. I showed you that in proteins. I can also do that in surfaces. So our version of epitaxy is putting oligonucleotide bonding elements on a surface and then growing structures from the bottom up. But you can do this in a really sophisticated way. For example, you can begin to create holes in resist that at the base of the holes, you modify with oligonucleotides that recognize particles. You can control the position, the symmetry, the orientation. So if I make holes, for example, that are cubes and control their rotation, I not only control the position, but the orientation of the cubes. They'll fit right in there and bond to the DNA at the base. And even facet directed. So these are octahedra that fit into these unusual shapes in a particular way so that they can maximize facet-facet interactions. And just to show you, this again is not cherry picking. We're not just looking at the best of a really low yielding process. Here's an architecture that we've made. When I first saw this, I thought that must have been made by e-beam lithography. It actually, the holes were made by e-beam lithography where the oligonucleotides were placed. If you blow this up, blow it up even further, you see it's a structure that spans very large areas. It's near perfect, where the cubes in this case are placed exactly where we intended them to be based upon the holes and the oligonucleotides that drive those types of interactions. So I believe this means that we're going to be able to make true device type architecture. Now you can think about interfacing these with device architectures. If you're wondering, does this go beyond 2 dimensions? The answer is yes, it does. We can grow crystals from these types of systems. They look kind of cruddy here because we're encasing them in silica. We haven't gotten as good at doing it as we do in solution. But you can see we can control the pattern and therefore the orientation of the crystal that ultimately forms, layer by layer, again, building the architecture, letting the DNA to do the work. Okay, so what do you do with these? I'll just kind of leave you with these thoughts. We think we're going to be able to do a lot. We're now moving into that kind of phase of development here. We know we can begin to, for example, position particles and use them as catalysts and think about cooperative catalysis. We've been playing with that through some relatively early demonstrations. We know from an optical property standpoint, we can build all sorts of structures that have unusual plasmonic properties. I talked about reconfigurable, or I mentioned it. I really didn't show you. Here's an example of building structures the way I described, epitaxially, that again, I don't know how you could make any other way. You can see different combinations of disks, cubes, and spheres, and they're stacked on top of one another with the oligonucleotides driving where each particle goes over large areas. And you can begin to use these types of architectures to create interesting reconfigurable optical metamaterials where, for example, exposure to different solvents, going from water, for example, to ethanol, can contract the oligonucleotides and control the spacing between the particles, therefore the optical coupling and the optical outputs. And even examples of me-resonant metacrystals have been made. And so, you know, how far can we go with this? We don't know. We know we can make lenses. These types of architectures have interesting lensing type properties. We've made optical mirrors where we can build structures that George Schatz has simulated, and we've actually made that are wavelength dependent reflectors. And we think we're going to be able to make things like lasers as well using this particular approach. But one of the reasons I like coming to Caltech, and especially in a more physicsy oriented type of place, there's a real challenge, I think, to the community to think about what we can do with this, but also to expand what your view of is what in terms of what's possible. So we kind of made the point of in the example over here, where we made these snowmen type architectures at the end of the paper, saying that, you know, physicists and a lot of the modelers have looked at what's possible based upon the tools that are available. E-beam lithography, for example, the architectures you can make. Well, these go well beyond what you could make in terms of any known tool at the time. And so expands the parameter set and the types of target possibilities. And we should look at that and kind of in a feedback loop, figure out with that particular community what sorts of targets to ultimately go after. And that's kind of where we are today. Okay, so I want you to just remember this then in terms of hopefully what you've learned. This, I think, is a really powerful way of building matter from the bottom up. I would argue that it's the most powerful form of crystallization on the planet. And the reason is very simple. Atom identity and bonding characteristics are separated. That gives you a type of predictability that you don't get with conventional chemistry. Programmable interactions, directional interactions through shape. I've talked about the bonding decoupled from composition. Once you have a design rule for making a particular crystal, as I said, if you swap out the identity in terms of composition, as long as particle size and shape are the same, you'll get it 100% of the time. Tunable bond length, every base you add, we know what the bond length increase will be, highly predictable. Tunable bond strength. I didn't talk about DNA flexibility. You can actually use that in certain cases to drive systems to unusual outcomes. We've figured that out with Sharon Glotzer. And I think this is really important too, that you can begin to use these bonds as functional entities. And you might ask, why would you want to do that? Well, recognition elements, for example, small molecules, metal ions, all sorts of things, and use the optical coupling changes to ultimately magnify the outputs of the response with respect to the molecular recognition event. May be an interesting way of creating all sorts of cool and potentially useful chemical sensors and biological sensing systems. Okay, let me finish by acknowledging a lot of the people that have done the work. I'm not going to go through this whole list. Lots of people over the last 25 years have begun to contribute to this field, either in the crystallization part of it or in terms of building alignment on DNA templates. At Northwestern and kind of within our own local community, these are the key people that have contributed to many of the projects that I shared with you today. George Schatz, Sharon Glotzer, and Monica Olvera on the modeling side of things. San Bin Win, very important, was actually a Caltech PhD student here with Bob Grubbs in terms of making some of the organic core spherical nucleic acids. Vinayak Dravid on the electron microscopy side of things. Youngdu Lee is really the key guy on the synchrotron X-ray characterization side of things, along with Michael Bedzik. Corey, who's also a Caltech product, came out of Harry Atwater's group. He's very important in terms of a lot of the modeling of the plasmonic properties and the driving towards different types of targets. And this guy, he was actually a grad student with me. He's now a professor at MIT. He's fantastic. He laid the groundwork for what I'd call the first step towards the design rules that I shared with you today. And I think really, created a path to something that goes well beyond phenomenological observation, but a set of rules that can guide many people for many years forward in terms of building programmable matter. And then this is the group at Northwestern. These are the key people. I've mentioned a bunch of them throughout. An incredibly diverse group of people that have come from all different walks of life and different disciplines and bring a lot of their talents to make the advances that I shared with you today. And these are the people that funded the work. And I always like to acknowledge the good people of Dubai who have adopted the spherical nucleic acid as the icon for their airport. Thank you, and I'd be happy to answer any questions.
Flexibility. I wonder, the spherical DNA, how deformable is that? For example, if you look at the dynamics rather than the static structure, surely there's lots of ways you could deform that structure in terms of entering cells and so forth.
Harry,
Yeah, okay.
I'm going to repeat this. Hold on. I'm going to repeat this question, right, for our Zoom listeners. So are you asking how flexible are these structures, or
About
the dynamics effects?
these structures and how deformable are these? How far can you push them outside the spherical DNA? How non-spherical can they become with rather weak interaction?
It's a very good question. Okay, so first of all, remember the spherical nucleic acid has got an inorganic core, which is solid, typically, at least the prototypical system. And then you've got your oligonucleotide shell, which is mostly water and salt. If you dry them out, oligonucleotides will collapse. There's enough to basically just lay on the surface. We know that because the interparticle distances in the lattices will go from 30 nanometers to 1 nanometer. They compress. If you don't dry them out, though, there is an electrostatically driven and density driven directionality. Right? We know that because we get all the pairing that we see, and we can build the architectures that I've shared with you. But that doesn't get at your question. The question is, if I have that system, is it very dynamic? And the answer is, it is in many ways. So if I take a lattice, for example, that's been made, and I apply pressure, it'll compress, right? That gives you a feel for the compressibility. And I can tell that because the optical properties of the lattice will change as the particles get closer together, in the case, for example, of gold cores. And then if I relax, it'll rebound back to the original state. So very flexible. Dynamic is really interesting. So Monica did a beautiful simulation, and it kind of changed the way I even thought about these architectures. Because I used to think about, like, you see these beautiful lattices, and I think of the particles as fixed in space, because when we encase them in silica, they are fixed in space. But in solution, they're really quite dynamic. So the way to think about this is these particles are constantly rolling around in these lattices. DNA bonds are broken and reformed, and you know that because that's how you get ultimately to those particular structures. It never stops, though. It's just once they've rolled into a thermodynamically preferred site, they've maximized the site, or they've maximized by going to that particular site, the number of duplex connections they have. And so when this guy breaks, I'm tethered over here. So now I might rebind to the same oligonucleotide or a neighboring oligonucleotide. And then this guy breaks, and it keeps going on and on and on. That's why we were able to make the electron equivalents. When you have a big particle and many oligonucleotides, The dynamic nature doesn't kill you, right? Because you've locked into a particular site, you've got it tethered down many different sites, and the breaking and reforming doesn't allow them to tumble. The tiny particle, where I might only have 4 to 8 oligonucleotides, when one breaks, I now can roll and find another site, and roll and find another site. So the smaller you go, and the fewer number of oligonucleotide connections you have, the more dynamic the nature of the particle is, and you move from that, that duality, where you move from what we call a programmable atom to an electron equivalent.
My second question is, what about the thermal stability of the crystals that you're making?
Harry, let me repeat this question so that everybody can hear what Chad is answering, okay? So the question is being raised about the thermal stability of these, of each individual SNA, or of the crystal already?
All those crystals.
Oh, the crystal, yeah, the beautiful lattices that you showed.
So for the as-made structures in solution in salt water, it will be so unmodified form. It'll be defined by the melting temperature of the DNA used to make them. So that can be moved from a little above room temperature to 50, 60 degrees. If I want to raise the stability, we use that silver ion trick, and that locks the oligonucleotides in. And now that I can go to 110 to 120 degrees. If I want to go to really high temperature materials, I lock the crystals into silica. I don't care about the oligonucleotides anymore. In fact, for many purposes, I want to get rid of them. I burn them out, and I can take that up to many hundreds of degrees, and I'm fine. So it all depends upon what you're calling the crystal. For the as-made structures, it's defined by the oligonucleotide interconnects.
All right, thank you. We have a couple of questions that came in through Q&A, so I'm going to
Okay.
read them off right now. So the first question is, everyone is saying thank you for the really enjoyable and inspiring talk. And the question is, do these lattices have similar electronic properties to what you would expect in a lattice, like conductivity? And then both in terms of the protein lattices and just the SNA ones.
Okay.
And do they? Sorry, so those are the first two, right? So are they electronically equivalent to what you would expect in a lattice? And then do they exhibit any bioactivity?
Okay,
That's all from the same person.
Let me answer the first of this. So the first question is, these are not great electronic materials. They've got big distances between them. They've got oligonucleotides that have N groups that are insulating types of N groups that are bound to them. And the distances are large. The system is really designed. Yeah, well, they're designed to modulate optical properties. They're ideal for modulating a lot of optical. So for that reason, most of the targets that we focus on have been optical and catalytic. I didn't talk about the catalytic. We've done quite a bit in the catalysis front as well. Is there a way to get to electronically interesting materials? Maybe, but it's going to require some tricks that we're trying to play that would allow us to make the lattice and then bring the distances to, really very, very close contacts, but the jury's still out there. On the bio side, for the lattices, I can't say we have big biological uses yet, but we haven't really explored them. We've been running with the particle cores themselves, the spherical nucleic acids themselves, down the biological front, and there are now many, many different commercial products based upon spherical nucleic acid nanoparticle conjugates, mainly in the diagnostic arena and also in the therapeutic arena. And I mentioned that at the beginning of the talk.
Right. But this is not a medical seminar, so that's why you're not sharing
That's
this
right.
with us.
That's a whole different talk.
That's a whole different talk. All right, thank you. Okay, this is a very complicated question. Let me just make sure I know how to read this. So this person says that atoms can form complex molecules with precise position of hundreds of symmetrically unequivalent atoms. Crystal structures made with SNAs are made from just a few symmetrically unequivalent atoms. Do you think you'll ever be able to make something nearly as complex as a 1920s organic chemist did with SNAs?
It depends on what you define as something. I would actually argue that the quasi-crystal example and the shape complementarity is pretty powerful demonstrations of being able to make structures that, 15 years ago, I would have told you there's no way you're going to make these, but now not only can you make them, you can make them by design.
Or you are able to design them in whatever.
Right, and I think the greatest chance of doing what he or she is talking about is on the protein side of things, where we're not just playing with the particle size and shape and isotropically functionalized structure, but where we can take a particle and place every bonding element exactly where we want, and now build a type of valency that frankly exceeds what's possible with conventional organic chemistry, because you have a lot more bonding interactions and a greater diversity of bonding interactions, which are defined by where you put the DNA, the length of the sequence, and the sequence itself.
And you don't have the poly exclusion principle.
No. Hey, but you know, the bottom line is these things are great in the sense that, you know, kids come in the or new people come in the group all the time. They say, you know, what can I work on? I said, well, you pick anything in conventional chemistry that we haven't looked at, and you create what would be the particle equivalent of that, and that's fair game, whether it works or doesn't work. Because I want to know, as I said, can we do it? Do we fall short, or do we exceed what's possible? And it becomes a really interesting straw man to drive where we go, at least from a chemistry development and material structure development exercise.
What are the void percentages in most of these? Are they 20% void space?
A lot larger.
Okay, I'm going to repeat the question. So what's the relative density of your crystals?
Yeah. So until we got to the high density architectures that I shared at the end with the shape complementarity, yeah, they're a tremendous amount of void space, right? Now, void space filled with a oligonucleotide.
Compressible.
Very compressible. And the other thing is, when you think of locking them into silica lattices and burning out the oligonucleotides, you actually create a lot of channel space to the particles, because it's not truly void space. It's filled with a oligonucleotide goop, you know, very sophisticated programmable glue.
Is that goop compressible?
Yeah, very.
So what's the?
So if you put it, you know, for example, if you put these into a polymer, you can use mechanical deformation to like an accordion to bring the particles closer and further, and they'll, you know, snap right back into the original structure.
Yeah. Yeah, I was going to ask about that. But sorry, did he answer your question?
Can you do cryo-EM?
Yeah.
Can we use cryo-EM to image these structures?
We can, and we do. Some of the images I shared with you were in fact cryo-EM. With the proteins, that's actually the choice. We can. So when we get down to the assembly of the proteins, we literally can look at it at the molecular level. We can see the proteins and the oligonucleotide bonds, which is really kind of cool. Again, that's what allows you to go beyond what we do with the inorganic system. So the proteins are really a neat test bed. We've had quite a few papers in the last 24 months on that topic. That's become a really powerful tool.
There's a question from your friend Rudy Marcus.
Oh, okay.
Okay. The question is, as you know, there have been a lot of single molecule conductivity. There's been a lot of studies that demonstrate a lot of single molecule conductivity. Some of it is in the far off resonance, and so they exhibit low conductivity. Have any of these systems been studied in that way? And if so, have there been any interesting results?
Unfortunately, no and no.
No, I know. Maybe that's your new direction.
Well, I know. I mean, in the sense that to me,
I guess it's an electronic question.
Yeah, exactly. These types, it goes back to the original question. These types of structures are not ideal for building electronically interesting materials.
But with the protein ones, you can dope them with redox active units.
Right, and you can get redox hoppers and.
Actually introduce electronic conductivity by putting in hopping stations with redox doping of protein.
But you always have the oligonucleotide shell, so you're going to have to deal with.
You have to break
with that, right?
Break through those barriers, yeah. Okay, here's a question from a different category. Once they're formed, can the SNA lattices be dried and retain their lattice structure? And if and can they be exposed to non-optical irradiation, for example, ultrasound waves, and exhibit some sort of resonance properties?
Yeah. So the answer is, in the as made way, I mean in solution, if you dry them, the oligonucleotides will just compress and fall onto the surface, and you lose most of the structure. But if you lock them into place using the silver ion trick or the silica, then you can do almost all of the above.
Okay. That was That was the last question that came in here. So can I now ask a question that I?
Good discussion.
Yeah,
It's
very good. Yeah.
excellent discussion. Can I now resort? Wait, can I ask my question?
Yeah, you can.
Okay, I'm sorry, I've been waiting and waiting. I'm like serving everybody else. I want to ask about the mechanical properties, of course. So these are lattices and they're very near and dear to my heart. And so have you at all tried to compress them, deform them, shear them, do anything with them?
Just the early experiments. Actually, it was last time Harry talked to us. He was talking about can we use these as
Which Harry?
force sensors? No, the other Harry.
And multiple Harrys in that row.
Yeah, we got a whole row of Harrys.
We have degenerate. We have a hairy degeneracy in the room.
I've never had a whole Harry audience. This is incredible. Yeah, so he was talking about using these as fluid sensors, and I think that's very, very not only likely we can do that. I mean, they're going to be very sensitive, and you can design them to be pressure dependent and use the optical coupling as kind of readouts for that. But we have not done a lot in that area. I'd like to.
Why don't you give them to us? We'll
I think we're ready. These guys. In fact, anybody. I would put the challenge out there. For anybody that has an interesting architecture, I said this to. Is it Andre? Said his name?
Probably.
Much, yeah.
Yeah.
If you have an interesting structure, even that we haven't made, and you're wondering if can it be made via this, give that to us as a challenge. We might say we can't do it, but if we can, we'll go to it. We like that. We want to figure out how far we can go with this. And better yet, if you can figure out structures, I look at this, we have a whole diversity of architectures we can make. What would be an architecture that would lead to a property? Because I think that's really where this is headed. The properties that can be designed in the materials with this type of control over architecture. Those are great targets for us, and we'd love to collaborate, and I think it's a mutual win-win.
I have a lot of interest in architecture. Okay, so I don't see any more questions coming in through the ether that we're all operating in. And Tiffany would like to point out that Rob McFarland was a KNI postdoc.
Oh, that's right.
So that's right. So
He's a
there's an
superstar.
extra connection in there.
Yeah, fantastic.
Yeah. And my student Daryl is a postdoc in his group right now. So it's all connected. All right. Is there anyone else in the audience besides Harry Graves who would like to ask a question?
Well, I want you to make electron physics.
I know. I'm.
Sounds like there are quite a few questions.
We're trying. It's tough though.
He's gonna make you choose a structure and then start on that process. Yeah. All right. Well, with that, I'd like to extend a huge thank you to you, Chad, for coming here and for this wonderful talk. And thanks to our